Assalamu alaikum dear students. Today we are going to discuss another type of integral, that is a definite integral. You know that the integral of the form of a to b integral f dx is simply the definite integral of f of x. Here this point a is called as the lower limit of integral and b is called as the upper limit of integral. You know that it simply represents the area under f between a and b. It has unique value because the area is unique. Now we shall introduce this definite integral either as the limit of sum or the value of the antiderivative of this small fx, which is let's assume that antiderivative is capital Fx in interval a and b. So firstly we will discuss this definite integral as the limit of sum. Now let f be the continuous non-negative function in interval ab. Now we are taking here this continuous function as non-negative so that its graph lies or its curve lies above the x-axis, like here. Now here a and b, the graph of this function f of x behaves just like, assume that it behaves like this. So this means that the integral, definite integral, that is integral f dx from a to b is simply represents the area under this curve, that is the area of this quadrilateral a b c d structure, not quadrilateral, it is structure. Now partition or divide this interval into disjoint subintervals as, now we partition this interval, that is main interval or the bigger interval, as the intervals x0 x1 x2 up to xn minus 1 xn, where x0 equals to a, x1 equals to a plus h, or xr equals to a plus rh, and xn equals to b, where this b we put this to be a plus nh, where n is the number of these subintervals which are disjoint. From this h becomes b minus a by n. Now as we partition this interval ab into infinitely many subintervals, that is when we let n tends to infinity. So what is h? H is actually the distance between these two points, endpoints of this tends to 0. Now if we consider an interval arbitrarily subinterval from this, like xr minus 1 xr, that is xr minus 1 and xr actually are the points on x-axis. Now the corresponding points on this graph are f of xr minus 1 and f of xr. Now here this PQRS is one rectangle and PQR1S1 is another rectangle. Now here the smaller rectangle, the length of its side is f of xr minus 1. F of xr, it's f of xr minus 1, while as the length of this rectangle is bigger rectangle is f of x, or simply f of xr. Now here area of this rectangle PQR is clearly less than area of PQR1S1. Now what is the length of this interval? It is xr minus 1, and let's put this to be del r, that is del r is the length between these two is the length of this subinterval. It is simply h. Now when del r tends to 0, now if length tends to 0, it is only possible when this h tends to 0, or when h tends to 0, length tends to 0. So when length tends to 0, this means that this rectangle actually, this rectangle, smaller rectangle, area of this becomes nearly or equal to the area of this bigger rectangle. Area of this bigger rectangle. Now we will use this very concept. Now when we partition this into subintervals, and in each subinterval we get two types of rectangles. Those rectangles which lies below the graph of f of x, and those rectangles which lies above the graph. So this means that the sum of all those rectangles which lies below this graph of function are represented as PQRS. So this means that the whole sum of such rectangles, now those that area is always less than area under f, because they touch slightly to this f, while as this area under f is always less than area of the rectangles which lies above the graph of f of x, that is sum of the areas of rectangles of the form of PQR1 S1. Now area of PQRS is actually f of x r minus 1, because its length is f of x r minus 1, and del r is actually the length of this interval, which is actually the breadth of this rectangle, which is f of x r minus 1 into h. Now the sum of all such rectangles, that is sum of the areas of all such rectangles, so the area of PQRS rectangles equals to f of x naught del 1. So this means for first rectangle, for first sub interval x naught x1, we will get the rectangle whose area is which lies below this graph. Its area is f of x naught del 1. Similarly, for second, it is f of x1 del 2, so on to f of xn minus 1 del n. Now let's assume that their sum is Sn, which implies that summation, we can write this in as a summation as summation all runs from 1 to n, because we have n intervals f of x r minus 1 del r equals to, now this del r is h always, so taking it out from this summation, so we simply get h all runs from 1 to n summation f of x r minus 1. Similarly, sum of the areas of the rectangle of the form of PQR1 S1. These are the rectangles which lies above this, or whose area is which lies above this graph of this function. Now its area is, now if we consider this interval xr minus 1 and xr, for this rectangle PQR1 S1, its length becomes f of x or not f of x1 or minus 1. So this means that for each interval we get Sn dash, which is whole area, equals to summation r from 1 to n f of x r into del r, which is h summation r runs from 1 to n f of x r. So clearly from this equation first, this Sn is less than area under f, which is less than Sn dash, because Sn dash represents the sum of the areas of the rectangle which are which lies above this graph of this function, and where Sn is simply the area of those rectangles which lies within this graph. Now as n tends to infinity, that is when we partition this interval ab into infinitely many intervals, their length becomes negligible. This means that h tends to 0. Now when h tends to 0, when length becomes negligible, this means that actually this difference, that is this difference here, this difference, it will tend to 0. When it will tend to 0, which implies that area of PQRS becomes area of PQR1S1. So this means that this Sn approaches to the area of f, and this area of and Sn dash approaches to the area of this Sn dash. This means that, but area under f is actually indefinite integral a to b f dx, which is limit n tends to infinity Sn or limit n tends to infinity Sn dash. But we know that h is b by a upon n. Now Sn dash, we will consider only here Sn dash. Sn dash is h summation r runs from 1 to n f of xr. Now f of xr is actually f of x1 up to f of xn. Now as n tends to infinity, this h will tend to 0. So we can write this as limit n tends to infinity Sn dash is actually limit h tends to 0 h f of x1 up to f of x1. Or if we replace h in terms of n, then we have to take h as b minus a upon n, and as h tends to 0, n should tend to infinity, which implies that in place of h we have to write limit n tends to infinity b by a upon n into f of x1 up to f of xn, or taking b minus a is out because it is independent of n, so we can take it out from the limit, which is b minus a limit n tends to infinity f of x1 up to f of xn divided by n. which implies that this integral a to b f dx is actually b minus a limit n tends to infinity f of x1 up to f of xn upon n, where this xi is actually a plus ih, or simply a plus I upon b minus a by n. So here you have to first replace this xi by a plus ih, then after simplifying this you have to again replace this h. You have to replace h in terms of n if you are taking limit n tends to infinity. Now if you are taking n tends to 0, h tends to 0, then there is no need to replace h in terms of n. So this means that this integral a to b f dx is actually limit h tends to 0 h into f of x1 plus so on to f of xn, where xi is a plus ih. This very expression or this very formula is called as the definite integral as a limit of sum. Like if we consider find the definite integral of x from 1 to 2 as limit of sum, or express this as the limit of sum, or solve this in terms of limit this sum of the limit. Here a is 1, b is 2, h is b minus a by n, we know it, which implies that h is actually 1 by n. Now as n tends to infinity, this h tends to 0. Now we know that a to b f dx is actually b minus a limit n tends to infinity f of x1 up to f of xn upon n, where xi is a plus ih. Now b minus a is 1, that is 2 minus 1, limit n tends to infinity f of 1 plus h, so on to f of 1 plus nh upon n. Now this f of 1 plus f of x is here x, which implies that f of 1 plus h is 1 plus h, f of 1 plus nh is f of n plus h. Here we are partitioning this interval 1 2 into n intervals, so this means that here we will have how many ones? N ones. So it is simply 1 plus 1 up to 1, n times is actually n, and h 1 plus 2h plus 3h plus nh. So taking h common, we get 1 plus 2 plus 3 up to n, but we know that sum of first n numbers is n into n plus 1, which implies that 1 plus up to n is n into n plus 1 by 2 into h. But h equals to 1 by n, so replacing here h by 1 by n, so n and n will cancel, we get n plus 1 upon 2 up divided by n, which is simply 2n plus n upon 2n, that is 3n plus 1 upon 2n. Now distributing this denominator, it is 2n upon 3n upon 2n, which is simply 3 by 2. It comes out from this limit because it does not contain n, and 1 upon 2n, limit n tends to infinity, which is simply 0. So its value is simply 3 by 2, because when n tends to 0, when n tends to infinity, 1 by infinity tends to 0. This means that the integral 1 to 2 x dx is actually 3 by 2 by the by limit of sum. We solve this as a limit of sum. So inshallah tomorrow we will discuss few more examples how to solve the given definite integral as limit of sum. So thank you.